what percent of volume is taken by saturated culture of bacteria. Okay, let's give a few options. It's like few tens of percent, which you remember we could write as this way. Or few percent, or point few percent, or much less. Okay, we're talking about like we had this, we put the bacteria, we let it grow, and now we come back, we have this muck of, some, yellowish bacteria, and the question is, what is the fraction taken up here? Who's voting for a few tens of percent? 10 people. Who's voting for few percent? 15 people. Point few percent? 5 people. Who's voting for much less? Nobody. That's interesting. Can you raise again who ever grew bacteria? Okay, the vast majority. Okay, so the vast majority grew bacteria, but the answer to this is not completely clear. And most of you are wrong. So that's good. Okay, so how do we approach this? Any ideas? Okay, so first option was about, you carry all this number about like how many cells are in OD, and then we could do the calculation for the number of cells. In other ways, related to this, you first know something about like doubling time, and from the doubling time, you can know number of cells, and then you do similar trick. Good. Other, strategies? Okay, so then you're saying, I have my intuition, I just, I centrifuge them, we look 1%. Okay, you're very good intuition, 1%. All right, okay, so first of all, I'll say, we had 3 suggestions. If I need to cluster them, they're like quite different in terms of their sensitivity to, like, if we do the calculations, there's all sorts of things that could go wrong at some calculations. Some of them are more robust. Which one do you think are the more robust one, and which one could go wrong? Right? Okay, good. Let's start with your approach. Okay? I never did it that way, so let's do it. How would you do it? He says, we start, with these things. Those who didn't do it, no worries. You might actually get a better answer than the others. So that's good. You're throwing in some bacteria that you scrapped from something. So let's say a few millions. There's a question how much we're dependent on what is the exact number, but we'll see. And then the next thing you're saying, it's 10, like, you left the lab. We won't tell your PI. You left at like 5 p.m. No, probably if you want 10 hours, you must have left like 8 p.m. and you came at 6 in the morning. Okay.
Saturation.
Because then they stayed in saturation. Okay, so you left at 4 p.m., 10 hours, and midnight they got into, or like 2 p.m., and then from there they finished growing. Okay, 10 hours, good. And then you're saying doubling, let's say 20 minutes doubling time. Okay, and you infer from that. Okay, so from this and that, you see what's happening here? 10 hours, and you're doubling every 20 minutes, so you have 3 doublings every hour. So altogether you have 2 to the power of 30 fold increase. Okay, what do we do next? Okay, so one trick is to say 2 to the third, which is 2 times 2 times 2, it's 8. 8 is like 10. I actually have a better one. Okay, just for the fun of it. How much is 2 to the 10? So it's 2, 4, 8. When I can't fall asleep, that's what I do. 2, 4, 8, 16, 32, 64, 128, 256, 512, 10,024. Okay, which is nice because that's like really close to 10 to the 3. Right? So you can impress your friends every time you want when you need to do these things. Every time you have 2 to the something which is large, you can take every 10 and make it into 3, and that's 10 to the 3. Very useful. Okay, so this is like 10 to the 3 times 3. 10 to the 9. Okay? Everybody with me, more or less? Feel free to ask. That's really the engine behind the good lecture. What's next?
So we get few to the power of few times 10 to the power of 15 bacteria, which is times micrometer to the power of the third, the volume of the...
So few times 10 to the 15 bacteria. Okay, so what do you do from here?
We infer the volume, which is 1 micrometer.
Okay, so far so good. You got the few 10 to the 15. And now we want to go from this to the volume that it takes. Okay? So how do you do that? Okay, so you need to take, this is the number of bacteria, and you want to multiply it by the volume of the bacteria, which is, yeah, so it's 1 micrometer times 1 micrometer times 1 micrometer. So it's 10 to the minus 6 meters cubed, which is 10 to the minus 18 meter cubed, right? Good? Okay, I'm sorry that I'm all over the place, but it's actually, I'm enjoying myself. Okay, what's next?
Next we need the volume of the starter.
Okay, so what's the volume of the starter?
Few milliliters.
Okay, so we're starting with few milliliters. That's the volume of starter. So what is few milliliters? Okay, it's few milliliters. Milli is a 1,000th of a liter. Few 10 to the minus 3 liters, which is
10 to the power of minus 6 meter cube.
fantastic. Few times 10 to minus 6 because I'm going from liters into meters cubed, and there's 10 to the 3 liters cubed per meter cube. What did we get for the volume of the bacteria? So we had few times 10 to the 15, right? Times 10 to the minus 18. So we're getting few times 10 to the minus 3 meter cube. Right? So, what did we get for the density? So, what is the result? I heard different things. So, I see some people looking like this. Yeah, so it's a bit confusing, right? We got not 0.1% what it seems. That would have been if we would be dividing this by this. But we're dividing this by this. Right? The density is the volume taken by the bacteria divided by volume taken by... Okay, so I really laid the trap for you, and you fell through.
We did a calculation.
So really what we got is a volume of bacteria much, much bigger than the volume of the starter. Okay, so, paradox. Yeah, so okay, so the Achilles heel of this calculation is sitting, these things could be sensitive, it sounds like a really good strategy. But then there's you're assuming like exponential growth. In exponential growth, things could go like crazily wrong. There's this example of if bacteria were growing exponentially, if I don't remember, 3 days, they would be the size of the moon, right? Or they would reach the moon, or both. So this thing of assuming 10 hours, 20 minutes doubling, which is sounds very sensible, is very, very dependent on whether you use 10 hours or 8 hours, 20 minutes or 30 minutes. It's highly sensitive to this. And these are numbers you don't know very well. You think that she didn't know well 1%. You know much, much less. This is much more sensitive to this. Because there, it's definitely true that she could tell between 1% and, let's say, 10%. or 1% and, point something. But here, like you have like this difference between 20 minutes and 24 minutes that would turn out to a much, much bigger effect in the exponential after 10 hours of that, okay? So there's this thing that is sometimes, not intuitive, but what is robust and what is sensitive? And you have to be aware of. Okay, so this method is highly sensitive, even though it sounds like very intuitive, and also it sounds like, very scientific, like very good, I put also, but actually it's much worse than the more intuitive thing. Okay, it's like, it got us 1,000-fold more than full saturation. Like it really got us like 1,000,000-fold or something wrong. Okay. I could say more about it, but actually that's already like couldn't be much better. Okay, we could do the other method that was suggested based on like this 10 to the 8, etc. It would be much better, but still could give you something wrong. I would say there's two methods which are much more robust and help you. One is this thing. Look at, it's about 1%. By the way, I think it depends. It could be somewhat less because they have usually you grow it in these flasks that look like this, right? And you fill it to here. And then you see they're here, right? And this looks like 1%. But then it's hard to say whether it's 1%, 0.1%, etc. Also because of the conical shape, etc. But you'll get roughly the right thing. And then you can actually do it in some other. Do you know like how much food do you give them when you're growing it? Usually when you make media. Anybody making media? At Weizmann, we're just getting it from microbiology, so it's too easy. But usually when you look at the recipe, it's like 0.2% or something like that. Like 2 grams per liter or something like that. What? 8 grams, maybe it depends on the recipe. Let's say you do it with 8 grams or 2 grams, etc. per liter. What does that mean? So it's 2 grams per liter. That's 0.2%. Okay, or 8 grams per liter, that's 0.8%. Okay? So that's what we're putting them in terms of food. What happens with that food? Some of it is thrown away, and some of it turns into new bacteria. Right? So how much are you going to get out of it? Less than the food you give them. So there's like no way it would be this. And actually no way it's going to be this either. It's going to be something like this. Okay, and also bacteria are not stupid. They're not just throwing it all away. So, this is the answer. And we could derive it in different ways, but I'm just showing you there's some robust ways to do it when you think about the essence, and there's some less robust, etc.